All right, so welcome back to EE4210. We'll get started, and starting this week, we will be talking about the data link layer. So we have finished transport layer and network layer. So now we'll go down the stack, and then we talk about data link layer. And as usual, our objective is to really first understand what are the features offered by, or the functions offered by the layer. So we'll first start off by looking at different functionalities, and then we will end up in looking at specific real-life protocols and see how they are implemented. Right? So in this case, today we'll start off by looking at error detection and correction. So when we were talking about TCP and UDP, we have looked at one version of error detection using checksums. So we'll talk a little bit more along those lines today. And then we will also look at the other main function that is provided by the link layer, which is how we share a link between different nodes. Okay? And subsequently, we will look at link layer addressing. So when we were talking network layer, we were talking about IP addresses. And in this part, we will also talk about a different kind of address which we also need. And those will be link layer addresses, which we also call MAC addresses, and then, so on. All right. And then we'll talk about local area networks and then specific examples of such things. So maybe first we get started off with an introduction to link layer, try to understand what it exactly does, what kind of services it provides, and then we'll move on to error detection and correction. Right, so this is a figure that we have seen previously many times. This shows you how an example network with different kinds, a home network and a cellular network and an enterprise at the bottom. So again, historically, different layers were developed by different sets of people. So the terminology they use is a little bit different, but then we'll try to keep a consistent terminology within this module. So in this case, at link layer, what we say is, the hosts, the routers, and so on, we all call them nodes, right? So previously we had talked about end hosts, and then we have talked about routers in the core of the net, right? So when we talk about link layer, usually everybody becomes a node. So this machine is a node. That Wi-Fi access point there is a node. A switch somewhere is a node. A Cisco router is a node. So these are all nodes. A node may have many different links coming in, right? So if you think of this as a node, it has a cellular link, it has a Wi-Fi, it has a Bluetooth, right? So those are all what we call links. So links are the communication channels through which we can communicate. We exchange data with somebody else. So we have links and then we have nodes, and these links can be of different types, right? So we can have wireless links, wired links, we can have optical fiber, and so on. And different links will offer you, of course, different data rates. And then the way we organize the link can be different. So for example, the Wi-Fi link here, we are all sharing. On the other hand, I could give you a piece of wire, an Ethernet cable, and that will be just dedicated for you. Nobody else will touch it, right? So the way we organize the links can also be different. And if you look at the standard documents and old papers and so on, a packet in a link layer context is called a frame. Just like packet was a segment in TCP, and a datagram in network layer, it's usually called a frame in link layer. But we'll just use the term packet, so we'll understand that. And the job of the link layer is to sort of move the packets or the datagrams from one end of a link to another end of a link. So this is a little bit an interesting thing to understand, and this sort of distinguishes your link layer from your transport or network layer protocols. So imagine a transport layer protocol like TCP, right? So what we have done is we have opened a connection from one end, one host, to another host. And no matter how many routers you pass through in the network, the TCP is still the same, no change. right? You have opened a TCP connection from, let's say, client to server. And all through the network, you're using TCP. It's the same TCP packet. The headers you have put in there, they don't change. They stay the same, and then you use your TCP connection. Last week, when we were talking network layer and IP, again, if you have started off with an IP packet, you go all the way IP to the destination. Of course, theoretically, it's possible, like we were talking IPv4, IPv6, but essentially, it's IP all the way. But the link layer is different. Link layer only takes care of, let's say this is a link that connects a computer. Let's imagine this. Right? Imagine this guy is on Wi-Fi. So there's a link from here to the Wi-Fi access point somewhere. So the link layer running on this phone only cares about how do I get the bits from this end to the Wi-Fi access point. It doesn't care what's going to happen beyond that. So a link layer protocol only cares about one end of the link to the other end of the link. So from the Wi-Fi access point, there'll be some other link layer protocol that will take care of sending the data from the access point to some switch or router in this building somewhere, right? So link layers operate on one link at a time. And from the source, let's say I'm doing Google, opening Google here, from here all the way to Google server, I will open a TCP connection. That connection will stay the same. But if you look at the link layer, there will be a different link layer protocol from here to the Wi-Fi access point. Then a different link layer protocol from the Wi-Fi access point to, let's say, NUS-IT. Then potentially a different link layer protocol from NUS-IT to Singtel and so on. Right? So link layer protocols can change on a link-to-link, hop-to-hop basis. So let me give you another example to sort of illustrate that. Right? So imagine, let's take an analogy from transportation. Right? So let's say I want to go to the Statue of Liberty off, Ellis Island between New Jersey and New York. So, if I were to go from here, I will first look up what is the best way to go, right? So if I search somewhere, maybe on the web, so it'll say, oh, you need to go from here to Changi, take a plane from Changi to JFK, New York City, and then, I made it up. Ultimately, to get to Statue of Liberty, you have to take a ferry or a boat. The boat doesn't leave from the airport, but let's say it leaves from the airport, right? So when I did the planning that I have to go from home to airport in Singapore to New York, then a boat, that's the equivalent of the routing protocol, right? So the routing protocol said, oh, you're going to follow this path. Done. But now to get from here to airport, Changi, I have to maybe, let's take a taxi. So that's the equivalent of the link layer protocol. In this case, the link layer protocol moved me from, let's say, NUS to Changi. And the protocol I used was a taxi. And then from Changi, I go to JFK. There's a new link layer protocol there, which is an aircraft. Okay, so my link layer changed. Path was decided, let's say. And then when I land in JFK, I get on a ferry or a boat. That's a different link layer protocol. So the same thing happens in the internet also, or in a general network. So as you move from hop to hop, so for example, here I can do Wi-Fi, and then the next one may be Ethernet, then the next one may be frame relay or PPP or something like that, right? So every link will do its separate link layer protocol. Okay, so now let's look at some of the services that a link layer protocol needs to provide. As with any other layer thing that we have seen, the application generates the data, gives it to transport. Transport takes that data, adds its own headers, right? UDP will add its own headers, or TCP will add its own headers. This whole thing, data plus TCP header, will go to network layer, IP. IP says, I don't know what is in there. Anything I got from upper layer, I treat the whole thing as my payload. I will add my IP headers in front. So now we have data, TCP header, IP header. This whole thing will be given to link layer. Link layer doesn't care what upper layer protocols are running. Whatever you've given me, as far as the link layer is concerned, that's the payload. Now it's going to add its own link layer headers in front, right? So that's your framing part. So you add link layer headers to get your job done. And so that would usually mean you would add a header. And so far in the protocols that we have seen, data in front, in the back, headers in the front. There are many link layer protocols. In addition to headers in the front, they will also add some information at the end. That's the trailer part. Okay? So depending upon the protocol, you may have a header. You may also have a trailer with that. So this part is fairly standard. Every layer sort of does it. It takes whatever upper layer gives you, adds its own headers, trailers, and forms a packet. On top of that, and this is usually one of the bigger things that a MAC or a link layer protocol does, it decides on channel access. So all of us, if you are on Wi-Fi here, we are all talking to the same Wi-Fi access point. So how does my phone know that it's now its turn to transmit? And how does your laptop know it's turn? Because if we both transmit at the same time on the same frequency to the same access point, there will be an overlap of signals at the access point. And we won't know what's going on, right? It's like if all of us start talking at the same time, you won't know who is saying what, right? So then how do we govern this? How do we know whose turn it is? So that's the channel access part. And this is only necessary if the medium is shared. So the Wi-Fi link is shared, so all of us are sharing it. In the old days, Ethernet used to be like that. So my first Ethernet when I was a student, it used to be a shared link. It was a physical piece of wire, but everybody would connect to the same piece of wire. Now things have changed. Now Ethernet is basically dedicated. You have a cable going from your machine to the Ethernet switch. Nobody else touches that. So that's dedicated for you. In that case, we don't need this channel access there, right? So depending upon which kind of link you're using, so the link layer protocol may have to do channel access, may not have to do channel access. But it becomes more interesting when we have to do channel access, right? Because things get more complicated and you have fun things to do. Also, it adds headers. And now we will talk about, well, not now, but maybe next lecture or the afterwards, we will talk about MAC layer addresses or data link layer addresses, sometimes also called physical address. And we will see why we need it, even though we have IP addresses on top. Right? Okay. Now, other things that the link layer may provide. For example, reliability. So I'm going to send from my phone to that access point. During this transmission, it's a wireless link. Right now we are in a room like this, but maybe I'm sitting outside in the corridor. Right now it's sunny outside, but imagine it's raining, right? So you're sending your data to the access point. There's a thunderstorm, there's a lightning, and that's going to create noise for you. And that's going to flip some of your bits. Some ones will become zeros, zeros will become ones, and so on, and your data or some part of the packet will be in error. So what should we do? Is it the link layer's job to fix it? Or should we say, oh, maybe you should have used TCP. Why didn't you use TCP? It's your fault. Right? So you can take different approaches to it, and then there are different link layer protocols which will either at least detect these errors for you, or then there are others who will not detect. They don't care. Whatever you gave me, I tried to send it. So, and the way we decide whether we should be doing error detection or not usually depends on the kind of link. If the link is more prone to having errors, then usually we add error detection. Usually wireless links. Wireless links are more susceptible to noise and interference. So most wireless links will usually do some kind of error detection for you. On the other hand, Ethernet copper cables and optical fibers and so on, they usually don't have that many errors. Bit errors are very, very rare. So to save time, of course, when you want to do these error detection and so on, you have to add some overhead, right? Remember, you have to add the checksum, for example. So if the errors are not that common, very, very rare, once in a million maybe, so then, we say, okay, fine, I'm not, for most of the time, I'm going to save on this overhead of adding the checksum, and I'll ignore that. So Ethernet and so on, they will not do error detection for you. So it depends on the kind of protocol. Wired links usually don't do error detection. Wireless links will do it for you. Okay. Now, you may ask why both link level and, you can say, fine, you have a wireless link, has more errors. So maybe it makes sense. But then you can say, oh, but we have TCP. Why would a network designer still implement error detection in the link layer when it's done at the upper layer? The answer is that, there is no guarantee that you're using TCP. Right? TCP is one of the available transport layer protocols. What if you're not using TCP? So maybe it's good to have some kind of error detection capabilities in other layers. Now imagine another scenario like this, right? Oops, I touched the wrong button. And this is more of a real life thing, right? So let's say this is my phone here, right? And I'm talking to a Wi-Fi access point. And this is connected to some router, to some router, to some router, to some router, and then, let's say, to a server. Okay. So this part is wireless. These are all wired. And let's say I'm using TCP. Fine. So what will happen in TCP? I will create the packet here. It will go here. It will go here. Ultimately, when it reaches the destination, this is where we will look at the checksum. Right? Checksum didn't match, so you say fail. You don't send an acknowledgement or do what TCP does, basically, maybe send a duplicate acknowledgement, whatever it is. Well, in this case, you won't, but yeah. So, and then some kind of feedback will come, and then you will retransmit. However, most likely the error happened here, right, in the wireless channel. In the first hop itself, your packet had an error. And you are sending this packet with error everywhere. And you know that ultimately it's going to be rejected at the destination anyway because it has an error. So essentially, you're wasting the bandwidth of the resources here, 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 and here. And then the packet has to go. TCP's error recovery process has to at some point figure out, maybe through a timeout or three duplicate acknowledgements, whatever it is, and then trigger the retransmission. So there's a delay associated with it. So not only are you delaying your recovery process, you're also wasting the resources along the way. So wouldn't it be better that if at the first hop itself, the AP detects, oh, there's an error in the packet, and tells it immediately, do a retransmission? It'll be much more efficient. Less wastage of network resources and also quicker recovery of the loss. So that's one of the reasons. Another one of the reasons why we may want to implement error detection at the link layer, even though it may be done at higher layers. Okay? And this particular diagram that I just drew, this is usually the standard network topology, in the sense that usually the wireless link is at the end. The links in the core of the network are wired, and they're higher quality, and they're more reliable. It's only the last hop, the hop that comes to the end user, that's wireless. Questions? All right. Okay, so what else? Other things that a link layer protocol can do, which is sort of similar to what we have seen before, is flow control. So flow control, again, is like, if the receiver is too slow, the receiver tells the senders, don't send so much, right? Now let me go back here. In the case of TCP, the flow control was here. Right? For flow control, we looked at the destination. Does the destination's buffer have enough space? The memory allocated to TCP at the destination, is the buffer becoming full? If it is becoming full, then the destination has to say, oh, don't send so much. And that's TCP, end to end. What about link layer? A link layer only goes from here to here. In the case of link layer flow control, if this guy's memory is becoming full, this guy will tell, don't send so much here. Similarly, this router also has a memory. If this is becoming full, it's going to tell here. Because link layer only works on, so the source of the link layer is on this side, destination of the link layer protocol is on the other end of the link. It's not completely end-to-end from the source to the destination. Okay? And this kind of flow control would usually be needed only at the very end, not in the main routers in the internet, which are very fast anyway, they don't have to worry. But imagine your Wi-Fi access point. There are, 50, 60 students around here, all connected to the same Wi-Fi access point. So for each of your connections, the Wi-Fi access point would have given you allocated some amount of memory for each one of your connections. If all of us start downloading or uploading videos now, the Wi-Fi access point is going to get into trouble. So then it will tell your device, slow down, or on the other side to slow down. So the concept is still the same of flow control. If the memory starts becoming full, we tell the other side to slow down. But now it's link by link flow control. All right, the other things that we have already talked about, the link layer can provide you are error detection. Errors are usually caused because of degradation in the channel. Two main things. One is when you transmit a signal, when it propagates, as a function of the distance, the magnitude or the power of the signal decreases. Right? So you may transmit at a high power here from your antenna, let's say. By the time it reaches the receiver, because of attenuation in the channel, the received power is very, very small. So sometimes it becomes difficult to detect what you send. And also, you're susceptible to interference from others. So this one works, so Wi-Fi works in a frequency band, which is called the ISM band, industrial, hang on. What is ISM? There's a medical, but see, that's the good part about having Google. I can search what is ISM band, though I should remember this. Industrial, scientific, and medical. Okay? So the thing is, so usually what happens with frequency bands? So let's say I want to transmit in a certain frequency. I want to do wireless transmissions. So can I just set up a radio and an antenna and start transmitting? The answer is no. I need permission from the government, and in Singapore, that will be IMDA, Infocom Media Development Authority. I have to go to IMDA and ask permission. Look, I have a very valid reason that I need to do this. Can you please allow me to do transmission in this particular frequency band? IMDA may or may not agree, or if they agree, they can say, oh, sure, you can transmit, but you have to license this particular spectrum frequency band. Give me money. So that's what IMDA does to, let's say, Singtel, StarHub, M1, right, when they do the cellular things. However, this ISM band is free. There are certain parts of the spectrum that are set aside, and you don't need any license to transmit. That's why you can set up this Wi-Fi access point at your home, and no one cares, because they're programmed to operate in a certain frequency band, which is free for everybody. If it is free for everybody, that's also a problem, because anybody can transmit while you're transmitting, and then there'll be interference. There are natural sources of interference, for example, lightning and so on. There are other man-made sources of interference. For example, let's say you live near a highway or a road. Even now, most of our vehicles are based on internal combustion engine, right? So we are transiting towards electric vehicles, but most of them still run on petrol or diesel. And what happens, I don't know if you guys have done your thermodynamics course earlier or not, but in a typical engine, there are 4 steps, right? You inject the fuel, then you compress, then you ignite, and then expansion. So there's a spark plug in your engine that ignites the fuel. But every time the spark plug fires, it also creates electromagnetic waves. And that's going to interfere with your Wi-Fi. Your roommate turns on the microwave, that's also going to cause interference with your Wi-Fi. You have a cordless phone at home, that's also going to cause interference with your Wi-Fi. They all sort of operate in the same frequency bands. Okay? So there are these. So now you have 2 options. One is you can just say, I'm going to detect if there is any error. And if there is any error, I will ask for retransmission. That's one approach. The other approach is, you transmit data to me. I will detect if there is any error or not. And at the same time, I will be able to correct it. You don't have to retransmit the data. Just by looking at some extra bits and so on, I will be able to correct it. So that's error correction. We can do it, but it involves additional overhead. So most of the time, we usually do not do error correction. It's just error detection, but people have figured out how to do error correction also. And then these links can be either half duplex or full duplex. So full duplex means you can receive and transmit at the same time. Ethernet is like that. While you're transmitting, you can also receive. Wi-Fi is half duplex. While you're transmitting, you cannot receive. So you can do one of those 2 things. Either you're transmitting or you're receiving. Hi. So before we move into error detection, so one last thing. So this is to talk about where is the link layer actually implemented. So the earlier 2 layers we talked about, transport and network layer protocol, they're all implemented in software. And usually they're part of your operating system. So when you install Windows or Linux or Android, that operating system comes with inbuilt code for TCP, UDP, IP, and all those things. So that's all part of the OS. And when you execute it, they're running in your CPU, and they're executed in software. So you fetch instructions one by one, and then you execute, right? That's the way. The link layer historically is done in a little bit differently. So link layer, part of it is implemented in hardware, part of it is implemented in software. And till maybe 15, 20 years ago, most of the link layer protocols, if you opened up your PC, of course there's a motherboard, even your laptop, right? There would be a motherboard. And then there would be a separate card for your link layer. Right? and we would call it an NIC or a NIC, Network Interface Card. So the network interface card is the one, or network adapter card here, that's what it's calling it, is the one that would implement most of the link layer protocol. So the network interface card would have just like we had seen in the router, it would have a physical termination for the link. So if it's an Ethernet cable coming in, you would have a socket of some kind where the cable comes in. And for Wi-Fi, it will be an antenna, right? So that's the physical end of the device. And then part of your link layer protocol will actually be implemented in a controller here. And there's dedicated chips you can buy, and these chips will execute, for example, Wi-Fi or Ethernet for you. The whole protocol would be implemented there. And to make things fast, these are usually done in hardware. So the whole protocol is implemented as a sequence of logic gates and so on. So you can do things very, very quickly. Okay? But then this controller would talk to the CPU and your memory through the main bus in your computer, let's say the PCI bus. And there's a reason for this, right? So for example, my Wi-Fi thing here, let's say my Wi-Fi is on. What it is doing, or even if it was Ethernet, what it would do is it's continuously listening to the channel. And anything the Wi-Fi access point is transmitting, this guy is picking it up. Okay. And then once it picks it up, it checks the address. Is it my address? If it is not, it throws it away. If it is my address, then I know this packet belongs to me, so it needs to go to upper layers. So at that time, this guy would usually send an interrupt or some kind of signaling to the CPU and then transfer the data from here into the memory. Okay? So imagine every packet that came in, whether it's for me or not, if I had to take help of the CPU or the processor, then the processor would be very, very busy just taking care of packets which don't even belong to me. So most of this processing and detecting whether the packet belongs to me or not is done separately in a separate piece of hardware. So we don't bother the CPU unless it's really my packet. Okay? So some part of the link layer protocol would also be implemented in the CPU. So for example, if I have to reassemble packets, some of the adding of headers and so on, that can be done at the CPU. But then when it's passed on for transmission, all those things, looking whether the channel is available, those kinds of things will be done at the controller itself. So the bottom line here is that the functionalities of the link layer are divided between a dedicated piece of hardware, the controller, and part of it is still part of the operating system. Okay. Operating system usually takes care of the things such as packetization, adding of headers, and stripping of headers on the reverse side. And the controller basically it takes care of interacting with the physical link itself. Questions? All right. And this is sort of what it is showing, what a link layer does. When the packet comes in, at the sending side, the CPU would encapsulate it, give it to the controller, and then we can add things such as error checking, flow control, and so on. And at the receiving side, we will do the opposite. We will see if there are any errors, whether we need to do flow control and things like that. And then ultimately, it will take out the MAC layer headers and give the packet to the network layer. All right, so that was sort of an overview of the link layer and the kind of services it provides. So maybe now let's go and look at error detection and correction a bit. Right? So the whole idea of error detection and correction is that so I'm transmitting channels over an unreliable link. So it is possible that some of the bits will be in error, so I need to be able to detect it. Now, nothing comes for free. So if you have the original data and you want to be able to detect or correct errors in it, so you have to pay the price, and the price is in terms of this overhead, and this is essentially your error detection or correction bits or code. And previously we have seen that this can be in the form of a checksum. So you have your original data, but you have to tag on some checksum bits to it. So the checksum was your overhead, and that was the price you were paying for the ability to detect errors in your packet. Okay? And so at the sending side, you will take your original data, add your error detection and correction, whatever you're trying to do, and then send it over the link. And at the receiving side, you will get some version of the data. Could be the original, could be some errors, so that's why it says D prime. And you will also get your error detection and correction bits. Again, they may be the same as what was sent on this side, or maybe there are some errors too. So that's why you have a prime here. And then you will have some kind of a logic to make sure everything is okay. If it is good, you can pass on the datagram to the upper layer. Otherwise, you deal with the error somehow. Okay. So while we have looked at checksums before, let's look at some other possibilities that are there. And here I will give you a very simple example of what could be an error correction option. Okay. So one of the earliest ways of detecting errors was through the use of parity bits or parity checking. And back in the 40s and 50s, we had some early computers. Though the hardware back then was very, very unreliable. So you can store something in memory, but by the time you read it, things can go wrong. So parity bits were commonly used. Parity bit is that in addition to the data, you have to add your error detection bit here, right? And you add a single bit. So the extra bit that you add is just a single bit. Maybe I'll do an example here. Let's say this is my data. Eight bits of data. What I will do is I will add one extra bit here, and this is my parity bit. And even here I have two options. I can do parity or I can do odd parity. The idea of even parity is when I consider all of these bits, right? The original data bits plus the parity bit. I will look at all of them. Then I will say the number of ones should be even. That's my even parity. So if I'm doing even parity here, I count how many ones are there. 1, 2, 3, 4, 5. So right now I have 5 ones. So that's an odd number. I need it to be even. So I'm going to add a 1 here. And if I was doing odd parity with the same thing, 1, 0, 1, 0, 1, 1, 0, 1, and let's say this is my parity bit. In this case, if I'm doing odd parity, so the number of ones should be odd. So here, already an odd number. So I don't need to add another 1. I will just add a 0. Okay. So how is this going to help me detect errors? So the way it will help is, so let's say I transmit this, and during transmission, this 0 becomes a 1. So at the receiver, what I get is 1, 0, 1, 1, 1, 1, 0, 1, and there's a 0 for the parity. Then now my decision making comes in here, right? So this part when I'm trying to decide if there's any error or not. And that is pretty simple. I just count the number of ones. So when I count the number of ones here, 1, 2, 3, 4, 5, 6. This is even. But remember, this was an odd parity example. Number of ones is even. This doesn't match, so I know that there is an error in here. There's an error in here. Now, you would be able to tell that, this kind of, this is detecting an error, but it has its own limitations. For example, what would have happened if 2 of my bits were in error? Let's say this had become a 0. If this had become a 0, so this would be a 0. So then I count 1, 2, 3, 4, 5. Now I get an odd number of ones, and I say everything is okay. So my error detection fails. Right? So now you can generalize this, and you can say that this kind of parity will only detect if there is an odd number of errors. If you have an even number of errors, cannot detect. Okay, fine. Single error, 3 errors, and so on, I can detect. How good is it in practice? In real life, what would happen? It turns out that in real life, when there is any error, errors tend to happen in bunches. It's not like I just have 1-bit error. Usually when there's an error, a whole group of bits will be in error. Why? Imagine the same thing, right? You're sitting outside and then you're using Wi-Fi to transfer your data. And then there's a lightning at the time. That lightning is not just going to affect 1 bit, right? The lightning is there for maybe few milliseconds or tens of milliseconds. During that time, it's going to affect all the bits. So in real life, errors tend to be what we call bursty. Right? So there's a burst of errors, and a whole bunch of bits would usually get affected. So when there's a whole bunch of bits which get affected, how big is a bunch? Whatever it is, it will be either even number or odd number. Right? Maybe it's 20 bits or 21 bits. Or maybe 50 bits or 51 bits. So you have a 50-50 chance. If you're doing odd parity, you have a 50-50 chance that, the number of bits affected will be either an even number or an odd number. So in that sense, the effectiveness of this drops down to 50%. Half of the time you're able to detect errors, half of the time you're not able to detect errors. And you may say that that's not good enough for me, right? So in reality, parity bits are not that commonly used anymore for detecting, but I just wanted to show you. And the other reason I wanted to show you is that this allows me to construct a error detection code, error correction, right? So how can I correct an error? In the previous example here, when I count and then the number of ones came out even, I knew that there was an error. But which bit was in error? That I cannot say for sure. Any of them could have been flipped. I just know that the number of ones came out to be even, so there's a problem. But I want to fix that error, so what can I do? So what you can do is, you have to add more overhead. Okay? So in this case, if you want to detect errors, these are your options. So let's say your data is like this, 0, 1, 1, 0, 1, 1, 1, 1. 0, 1, 0, 1, 0, 1, 0, 1. Something. Let's say these are my 4 bytes of data. Okay? And let's say we are doing even parity. So let's count 5, 6. So there are 6 ones, so I don't need to add anymore, right? It's already even number. Here I have 1, 2, 3, 4. Oh crap, I think I made all of them even, but anyway, doesn't matter. So here 1, 2, 3, 4, already an even number, no need to add anything. 1, 2, already an even number, no need to add anything. So this is my usual way of adding parity. But now, since I want to detect, I will also add parity for every column. Just like I was adding a parity bit for every row, I'm going to add a parity bit for every column. So let me add those parity bits here. If I look at the first column, there's only a single 1. So I need to add 1 more, so the number of ones is 2, an even number. In this case, I have 3 ones, so add a 1. Here I have a single 1, so add a 1. I have a single 1. Okay, fine. So 1, 2, 3 ones, so I add a 1. I made a bad example. Anyway, 1, 2, 3 ones, so add a 1. Okay, finally. So there are 2 ones, so I don't need to add. There are 2 ones, so I don't need to add. All right? So what I have now is a DIMEN, 2-dimensional parity. So how is this going to help me correct an error? So let's pick any bit that we want, and let's say that's in error, right? So I don't know what you want. So let's say this bit is in error. So this has become a 0 during transmission. Okay? So what I will receive then is like this. 0, 1, 1, 0, 1, 1, 1, 1. And on this side there's a 0, 0, 1, 0, 1, 0, 1, 0, 1. On this side there's a 0, 1, 1, 0, 0, 1. And now this is in error, so I have a 0 here. 0, 0, 0, 1, 0, 1, 0, 0. And here I have 1, 1, 1, 1, 1, 1, 0, 0. Right, this is what I will get, and this will be a 0, this will also be a 0. So now I will check at the receiver. Right, so this is at the receiver. This is what we have received. So we go every row, 1, 2, 3, 4, 5, 6. So no error here. 1, 2, 3, 4, even number, no error. 1, 2, 3, odd number. So I know that there is an error in this particular row. Right? So I know that there is some problem in this row. Right now I can't tell which one has the problem, but I know there's a problem. And now here, next row, 1, 2. Okay. Now I go column by column. 1, 2, this column is okay. 1, 2, 3, 4, this column is okay. 1, 2, this column is okay. 1, 2, column is okay. 1, 2, 3, 4, this is okay. 1, 2, 3, odd number, not okay. 1, 2, okay. 1, 2, this is okay. So I know that this particular row has a problem. And the intersection of the row and the column is at this bit. So I know that that is the bit that has a problem. So now I can change that 0 into a 1, and I have corrected my error. So in this case, I don't need to ask the sender to retransmit the data. Just by, on the receiving side itself, we can correct the data. This is a simple example. Again, you can easily create examples where this will fail. If you do more than 1 bit error, you can easily create where this will not work. But for simple cases, this will work. And there are many more complicated ways of creating error correction codes too. But in real life, what we usually do is, if there is any error, most of these kinds of schemes are good at fixing one error. If you have more than single bit, if you have 3, 4, 5, 6 bits of error, these things don't work so well. And like we mentioned previously, in real life, our errors tend to be bursty, so more than 1 bit in error. So these are not very useful then in real life. So while it's good to know in theory and real life are different. Yeah?
Is there a use for the bottom right?
You mean this corner one? This guy?
Yeah.
So I think what would happen is, it is possible that some of your parity bits may also be in error. Right? So there's no guarantee that this will always be transmitted correctly. So you can use this for detecting that. Okay. All right. So this is one. Right? So previously we have looked at checksum. Then parity bits are a second way of doing error detection. There is a third one that is commonly used that I don't have in the slides, but since we are talking about it, we can. That is called a CRC. All right. Cyclic redundancy check. And again, here the idea is still the same. Just like you had your packet, right? So you have packets, you have some headers, and you have your data here. Right? So even in CRC, what you're going to do is, you're going to look at your data, and you're going to do some kind of computation on it, and you're going to add some extra bits here. And at the receiver, you'll do some kind of check. Now, the actual method is a bit more complicated, so we don't want to spend so much time on it, but I'll just give you a very basic intuition how this works. Okay? So the intuition is this. Let's say this data is something. Like this, right? Again, let me use my machine and convert this to decimal. What did I write? 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 0, 0, 2 decimal. Oh crap. It didn't take that big a number. Come on, how do I do such a big number too? Anybody can do this for me? 0, 1, 0, 1, 0, 3 ones, 1, 0, 1, 1, 0, 1, 1, 0, 0. If I don't get it, I'll just make up a number for it. I can't get it, but it's okay. Right? So let's say this is equal to something. 9,436 maybe. So let's say that's my data. Now both the sender and the receiver, they have to agree on another number. So you both have to know this. Okay? So let's say that number is something, let's say 29. This is a number we both know. So what I'm going to do is, at the sending side, I will divide 9436 by 29. Okay, I will divide, and hopefully there's whatever the remainder is. This one I think my computer, my phone can do. 9436 divided by 29. The remainder is 11. Okay. So what I'm going to do is, I'm going to put 11 in here, the remainder. The binary version of 11. At the receiver is going to get whatever the data is, and it should get 11 here. So what the receiver will do is data plus CRC. I'm sorry, data minus CRC, let's say. And then divided by 29. And then it will see what is the remainder. Is this equal to 0? If it is not equal to 0, it says there's an error. If it is equal to 0, it says no error. And the whole idea is that if any of these bits is changed during transmission, or a sequence of bits is changed during transmission, this value would change. And so when we divide by this number, the remainder will not come out to be 0. So at the sending side, I have the number and I have the remainder. So if you subtract the remainder from this and you divide by 29, of course the remainder should be 0. Okay? And here I made up this number 29. There are many well-known numbers that we use. They can be either 8-bit, 16-bit, 32-bit, 64 bits, and so on. But the basic idea is this. And these CRCs are the one that are mainly used, let's say, in Wi-Fi and also in Ethernet and things like that. Yeah. So 9436 is that data. It's not, because my phone failed to, but I'm pretending that 0101, 011, all that thing converts to 9436. Yeah. But Google didn't convert for me, and that's the whole idea. Yeah. Yeah. It can. It's just that the probability of getting the same remainder, or a remainder of 0. So my bits are changed in such a way that even when I do the division, the remainder comes to be 0. That probability is very, very small. Comparatively, it's much more easier for me to construct examples where your checksum will work out, even though there's an error. So this is more robust against random changes and so on. And there's a lot of work that has been done. So people have, so I picked 29 somehow, right? There's a whole science for picking that number. And you don't pick any number at random. So if you express this as a polynomial, it has to satisfy certain properties. So for example, the last bit should be 1 and so on. If you choose that number 29 properly, then you are guaranteed, for example, that any single bit error, it will detect. Any 2-bit error, it will detect. Any even number of errors, it will detect, and so on. So your choice of that number and the likelihood that by luck, your bits are flipped in such a way that it's much, much smaller than checksum. Much more robust against noises. Yeah. All right. Okay. So that was sort of our error detection. So maybe let's get into multiple access protocols to start with today, and then we'll continue. I don't think we'll be finishing this in any way. So let's talk about multiple access protocols, right? So in general, we have two kinds of links. The first one is a point-to-point. So a point-to-point is basically one end here, one end there. So one end of the link is one node. The other end is another node, and nobody else is sharing that link, right? So, for example, in the old days, if you had a wired telephone at home, right? If you had a traditional phone, you had a phone line or a phone wire coming to your home, and that wire would go to the telephone exchange. Nobody else touches that wire, right? So that would be an example of a point-to-point link. These days, Ethernet cables are like that. The Ethernet cable that goes from my computer to the Ethernet switch, nobody else touches that. So it's my own dedicated cable. So you have those, right? And then the other option is, so these are a bit simple. Of course, there are specific protocols that tell you how to handle that, and PPP is one of the most common ones. And then there's another class of links which are broadcast. So in a broadcast, when you transmit, your link is shared by many others, and they can also listen on at the same time, and they can also transmit at the same time. So these are a bit more challenging in terms of rules, in terms of governing who transmits at what time. And if by any chance two nodes transmit at the same time, how do we handle that? Okay? And common examples are, in the old days, Ethernet used to be like that. We would have a single coaxial cable running, let's say, through the lab. And every computer would also take a cable and physically tap onto that same piece of cable. Right? Your wireless channels, such as Wi-Fi, are also shared channels. Satellite links can be shared links, and so on. There is a special name that we give to the link layer part, which takes care of these shared channels, and that is called a multiple access protocol. So since multiple hosts or nodes are allowed to share the same link, so there should be some rule to govern who transmits when, and these are called MAC protocols, or multiple access protocols. And there are two things that we need to worry about. Well, the main thing that we need to worry about is if two or more devices transmit at the same time, then we'll have a problem. And the term for this is called a collision. So collision happens when two nodes transmit at the same time, and the receiver gets both signals at the same time, so it cannot distinguish who is sending what. So what should we do when we experience a collision? That's one of the bigger challenges. And in order to handle this, we have our MAC protocols. And again, when we do these MAC protocols, you have two options. One is you can have a centralized node, a central controller that tells who gets to transmit. That's sort of the protocol in this classroom, right? If you think about this, we are all using the same shared channel, right? Because if we talk, our voice is in that 0 to 20 kilohertz range, or actually voice is probably between 0 and 4 kilohertz. If all of us start talking, we cannot make out who is saying what, right? But what is the protocol here? The protocol here is that the professor is sort of controlling the whole thing, right? So I'm the central controller. So I talk most of the time, and occasionally I say, okay, any questions? And your part of the protocol is you raise your hand, right? And in case two people want to ask me a question, you both raise. Sorry, who is calling me? Yeah, if two people transmit, what was I saying? If two of you want to ask me a question at the same time, you both raise your hands, right? And then I pick. Maybe you go first, and then you go next. So that's the protocol here. So that's a central controller. I'm controlling it. It's possible here. But what about in a wireless link? You're all sitting in this room. Who would be the central controller? You could say maybe the access point, possible. But ideally, we prefer a distributed algorithm. That means there is no single boss. Each device can figure out on its own what to do. Ideally, we would prefer that, right? So what happens if your central controller goes down? Then the whole network will go down, right? So in that sense, we would, come on. I should shut it down from, sorry about that, yeah. I kept losing my train of thought. What was I saying? Yeah, but yeah. So anyway, so we would tend to prefer the distributed one. That's fine. But in general, if we want to figure out who gets to transmit, right? You would think that maybe it will be good to sort of coordinate amongst us, right? If we could somehow coordinate, maybe all of us in this room, we say, okay, I will go first, you go second, and so on. How can we coordinate? We have this single air between us, right? How about if we had maybe a Wi-Fi walkie-talkie between all of us, right? So we could use the walkie-talkie to communicate and then say, this is the way we will schedule our transmissions. So that is what is called an out-of-band channel. Maybe walkie-talkie is not a good example. Maybe if I take this, maybe I send SMS messages or WhatsApp messages to all of you, and through this we decide when we can speak with our mouth. So then this one would be an out-of-band channel. But in a regular network, we don't want to have two separate networks to control one network, right? So usually we don't want this out-of-band channel for coordination. Just to set up this Wi-Fi link, I don't want to have another wireless link that will tell each other when to transmit. But in the old days for telephones and so on, it was actually used that in addition to your voice signals, we would have some other control signals that will control things, right? But for Ethernet, Wi-Fi, we don't do that. Any controlling that needs to be done will be done using the same channel. Okay. So now let's come to what we want. So you are the designer for this multiple access MAC protocol. What should be your goal? Right? What should be your design objective? So let's say the channel can support a rate of R bits per second. It has some maximum data rate. Right? So these are things that I would like, right, in my protocol. One is, if there is a single node who wants to transmit, like right now I'm the only one talking. So if there's a single node who wants to transmit, ideally it should be able to transmit at that full rate. Right? Let's say for some reason nobody else wants to talk, I'm the only one who wants to talk, I should be able to talk at full rate. However, if there are many others who also want to transmit, let's say there are m others who also want to transmit, in this case my protocol should be fair and everybody should get R over m, right? An equal share of the channel. So two things. One is, I want my protocol to be fair. If more than one, it should be fair. But then, if others don't want to use it, I don't want to waste my resources. Right? It should be efficient. If there's only one person, give that person the full data rate. Also what I want is, I want this to be fully decentralized. I want to design a decentralized protocol. That means there should not be any particular special node, no central controller. And also, I want it to be simple. I don't want any requirements such as, our clocks should be synchronized. Ideally, there should not be anything like that, right? It should not be like, time will be divided in slots and we know exactly when time starts. Because your clock, my clock, in an actual computer can be very different. Even if we are off by a few milliseconds, things will be desynchronized and then it doesn't work, right? So ideally, we should not have all of these things. Now, in terms of actual protocols, you can break it up into three classes. And the first one is channel partitioning. This is something we have seen before when we are doing the first set of lectures. And in this, what we do is, whatever resources we have, we break it up into individual pieces, and then we allocate to every user. Time division multiplexing, frequency division multiplexing, right? We'll come to that. Then there are some things which this is easy to understand. This is to say we take turns. Somehow we will have a round robin or some other mechanism. We can take turns. And then the one in the middle, this is the more interesting one and the more common one. This is random access. And here it's like, it's a bit of a free-for-all. You transmit whenever you want to transmit. Maybe there are some rules, but more or less you can transmit whenever you want to transmit. But if I let anybody transmit whenever they want to transmit, there will be collisions. Cannot avoid. So we will have to deal with collisions in that case. Okay, we'll see how we do that. So let's look at the very simple ones. So channel partitioning, this is something we have seen before. So the first one is time division multiple access, let's say. In this case, we have our channel, and I break up my time into slots. This is not so good, because now we are dividing into slots. Every user needs to know when a slot exactly begins and when it ends. If clocks are not synchronized, we're going to have a little bit of problem. Right? But anyway, let's say all those things are done. So I divide my time into slots, and in this case, I've divided my time into 6 slots. And I have 6 users. So I say user 1, you get the first slot, user 2, you get the second, third, fourth, fifth, sixth, and so on. And then this pattern will repeat in every frame. Now, I had 2 requirements, right? If there is a single user, the user should get the entire bandwidth. And if everybody is, let's say there are 6 users, everybody should get 1 over 6. So if everybody is active, everybody gets 1 over 6. Very good. But in this example, let's say there are three users who are active. So even though user number 2 is not transmitting anything, we have still allocated a slot for that user. Similarly, for user 5 and 6, we have allocated a slot. So this is not very good when only a small number of users are active in the network. Then you tend to waste a lot of resources. However, if the network is quite loaded, everybody wants to send data, then it's very good. There are no collisions because everybody has a dedicated slot. And if everybody is transmitting in their slots, the network is fully utilized and everybody is getting 1 over m. Okay? So these kinds of things are very good when the network is heavily loaded, but not very good when the network is lightly loaded. And of course, we have the requirement of synchronization and things like that. And then your other option is to go for frequency division multiple access. In frequency division multiple access, you take your resources in terms of time and frequency, and you break up your frequency band into smaller subbands. And you allocate one of those subbands to each user. So now every user can transmit all the time, but not over the entire frequency band. You have to stick to your smaller frequency band. In time division, you transmit over the entire frequency band, but not at specific slots. Here also, everybody gets 1 over m. Right? Because I have broken up my frequency band into, let's say, 6 parts here. Everybody gets 1/6 of the band. So your data rate is 1/6. But again, the same problem. If user 2, well, user 5 and user 6 is not here, but let's say if the 3 users are not active, we are wasting their resources. So again, this is good when the network is heavily, but maybe not so good when the network is lightly loaded. Yeah. Any questions on this? Yeah. I don't think I got your question. So in TDMA, I have broken my thing into time. And I allocate 1 slot to every user. And here, I break my frequency into bands, and I allocate 1 band to every user. So now, I'm constraining you to one of those smaller frequency bands. You can transmit all the time in a small frequency band. Okay, so if I understand you right, what you are saying is, why do I have to here I have given that slot number 2 to user 2, but user 2 is not using. So why don't I do something like, when user comes in, then I allocate. That's what you're saying, right? So you could do that, but then you would need a central controller. Right? You come in, at that time you have to request. That person will say, oh, this particular slot is yours. Previously, maybe, these 3 slots are unused. So one option is you give this to user 1, you give this to user 3, and then you give this to user 4, just to use up your unused slots. But now user 2 has come in. Which one should be for user 2? Or you have to tell user 1 that that slot is not yours anymore. Who will do that? Somebody, right? So you can do that, but it's not centralized anymore. It's not distributed anymore. Okay? When I put my phone there, this particular phone, when your phone talks to the base station, it actually uses something like this. But it's a little bit more complicated. It's a mix of both time division and frequency division. Right now, I'm not making a call. No time slot has been assigned to me. But the base station actually knows I'm here because periodically I tell the base station I'm there. When I will make a phone call, at that time the base station will allocate a time slot to me. And when I'm done, it knows I'm done, and it'll tell me, you don't get that slot anymore, and it will give that slot to somebody else. But there is a cellular base station out there, which is a central controller that's taking care of all of this. It's not a distributed protocol. Good? All right. Other questions? All right, so it's 11:24. I think this is a good time for us to stop today. And then when we come back Friday, we will take on random access protocols.